Hi guys, this is the video where I solve this set of exercises, okay, where you have to actually get a gradient vector doing the first partial derivative of every variable for a function, of course, and also get the Hessian matrix doing the second derivative, also regarding every variable. So, well, that is what I'm gonna do, so I hope this is actually helpful. I'm gonna take my face off the video, so anyway, I'll try to be clear with my explanations because I know this is sometimes not so easy. Anyhow, first function we have is f1, okay? So I'm gonna write here the function, even though we have it there, okay? And we have two variables, x and y, and the function is sine of x, y, okay? So first thing we do is the gradient of f1, which means we had to do the derivative uh, in respect to x and in respect to y. And so what we have here is actually the cosine of xy times the derivative of whatever is inside. So when we actually perform the derivation or in respect to x, what we have is y, and when we do it the other way around, what we have is x. And so this is it in both cases. In respect to the Hessian matrix, which is in this case four derivatives, okay, first we have this first one in respect to y, uh, and this sorry, in respect to x, and then in respect to y, and then this one in respect to y, because in respect to x is exactly the same. So what I'm going to do here is actually do the only one that is actually difficult, which is actually the first one in respect twice, first in respect to x, which is this function, and then in respect to y. Why is this one the only one difficult? Well, it's actually in the kind of function we have, it's actually the same of this. It's the same as doing this. It's the same as performing this derivative and then performing the derivative of this function in respect to x. We're gonna see, okay? But anyhow, I'm gonna do only one, so I'm gonna do the derivative in respect to y of this one. And this is actually a little bit more complicated than the rest of the derivatives because actually we have a product here of two functions. So um, we have to follow the rule of the product, okay? So in the first case, we have uh, the derivative of the first term, we have two members here that are actually multiplying. And so we have the derivative of the first member, which is actually sine of xy times the derivative of whatever is inside in respect to y, so x, times the second member without applying any derivative, plus cosine of xy, which is the first member without applying the derivative, times the derivative of the second part, which is 1, so which is something I'm not going to write. So this is the derivative that goes here, and also the derivative that goes here, because these two are actually coincidental, okay? In fact, when I do it the other way around, you'll see. If I do the derivative of this function in respect to x, so instead of actually solving this one, I'm going to solve this one. As I said, in this kind of function, these two are going to be coincidental. If I do this one, I'm going to do it here, okay? So, y and then of x. This is actually this, so this is minus sine of xy times the derivative of whatever is inside, and this is in respect to x, so this is y, and then second term like that. So this is actually the same you can see here, and then the other part is actually very easy, which is actually the first part without the derivative, which is again cosine of xy, and then times the derivative of whatever it is at the end, and so this is actually 1 again, and so of course they are coincidental. Okay, so I'm gonna just write here what derivative the derivative that we have to write here without writing it because we don't have a space. Okay, so in respect to y and then to x, and here f1 the derivative first in respect to x and then in respect to y. But these two, as I said, are coincidental. The other two are actually much easier, okay? In this case, if we perform the derivation in respect to x, we actually have a constant here, which is y, and then so we have actually the same as before. But in this time, like y is gonna come out again, multiplying everything, so it's gonna be y squared times cosine of xy, and here is going to be x squared times the cosine, times minus sine, times minus sine, times minus sine of xy. I'm sorry because here it's sin, because in Spanish it's written like that, but I know in English it's sin, and I don't think it's very important, but sin of xy. And so this is actually what it is, okay? Because the x goes out again here, so the same happens here with the y, because here x, when you actually perform the derivation in respect to y, is just a constant multiplying. The same happens with y here when you actually perform the derivation in respect to x. So this is what you have, okay? And this is the Hessian matrix. Let's go with the second one. Yes. Second one. Second one is this f2. Now we have a little more space. This is just e to the power of 2xy, okay? And so the gradient of f2, remember the derivative of e to the power of something just remains like it is, but then you multiply it by the derivative of whatever is uh, inside in the exponent, so exponent. So this is pretty much what you have to do here. And so you have, in both cases, you have the gradient, of course, and so you have two first derivatives, and then you have e to the power of 2xy. And so here we are actually performing the derivation in respect to x. So what comes down is 2y, okay? And here is exactly the opposite. So 2y times 2x, and that's pretty much what it is. Second derivative and the Hessian matrix of f2. I'm gonna leave some more space, although I don't need it, but same thing as before. In this case, when I perform the derivation of this in respect to x, like what I'm gonna write here, no product, nothing, because this is a constant. So yes, I just have 2y times e to the power of 2xy times what? Times 2y, right? Because it comes down again. And so instead of 2y, I'm gonna have 4y squared times e to the power of 2xy. And here I'm going to have this 4x squared times e to the power of 2xy. The other two derivatives, the derivative of this first one in respect to y and the second one in respect to x, there we have a product. We have two functions of y in the first case and two functions of x in the second case. So it is it has a little bit more of kick, uh, maybe a little bit more of difficulty. I don't know, but anyhow, I'm gonna do this one, okay? So what we have here is actually a product. So we do exactly as we did before. First is the first member, which is this one, and the second member is this one. So first member applying the derivative, which is this times 2y, and times 2y because it's a second member without applying the derivative, times, sorry, plus, um, first member without applying the derivative, times second member applying the derivative. So this is 2. And so what we have here, actually taking out the common factor, is, yeah, here we have actually, I'm going to write it again, so this is 4y squared times e to the power of 2xy plus e to the power of 2xy times 2, right? 2 like that. So this is actually 4 y squared plus 2 times e to the power of 2xy. This is pretty much what it is, okay? This is the common factor, and so that is where it is. And this goes in these two places. In these two places, that goes. And I'm gonna write it now. 4y squared plus 2 um, yeah, mm, times e to the power of 2xy. Yeah. Oh well, yeah, I see, I made a mistake. Mistake is that when I apply this part of the derivative here, what I had to bring down was not 2y, it was 2x. 2x, okay? Because what comes down here is actually 2x. So this is not 4y squared, this is actually 4, sorry, this is 4xy. And so here it's 4xy, and here it's 4xy. 4xy and 4xy. Yeah. I was thinking that like that it wouldn't be the same for x and y, so I had to be making a mistake. So that's what I look for. 4xy plus 2 e to the power of 2xy. Okay, that's pretty much what it is. I hope I didn't make any mistake, but well, it's always possible. Okay. Anyhow, now number three, f3 of xy, which is e sorry, e to the power of x times y. So the gradient here is just n gradient is just like before, okay? We have two functions of different variables here. So either this is going to be a constant when we apply the derivative thinking of y, or this is going to be a constant when we apply the derivative thinking uh, about x as our variable. So when we actually apply the derivative of x, this is e to the power of x times y as a constant. And when we do the other way around, this is y, which just becomes 1 times e to the power of x. And so here we just have e to the power of x, just like that. And so as this didn't change, as we see, the Hessian matrix is going to be actually pretty easy, because here we actually have an easier function than before. And so when we actually perform this derivative in terms of x and y, the results are going to be these two. And so this is in respect to x. And so what we have here is that this is actually y to the power of e times e to the power of x. And here and here, this is going to be uh, the function, right? Because when we actually perform this derivative in respect to x, this is what we get, okay? This is what we get. And when we perform this derivative, sorry, when we perform this derivative in respect to y, this is what we get. And when we perform this derivative in respect to x, this is what we get. So yes, what about this? Well, this is just 0 because the derivative of this last function in respect to y is nothing. We don't have any y there. So just goes blank. And so this is the Hessian function, okay? Well, let's do it. Okay, now, yeah, number 4. F4 of x, y. This is 3/4 of x, y here, okay? This is something I sometimes do, but I never use this as an example because we usually work with the natural logarithm. or Neperian logarithm as we say in Spanish. And so when we actually do this, what we have is the following. Okay, is the this is exponential without the e. We don't have number e here. We have 0.75. It doesn't matter because it's actually pretty much the same. We actually do we keep that as it is. 0.75 to the power of xy times the derivative of whatever is here, so times y, times the natural logarithm of whatever was in the base. So here times the Neperian logarithm of 0.75. So that is it. That is the first one. What about the second one? Well, exactly or almost exactly the same, which is 0.75 to the power of xy times x times the natural logarithm of 0.75. And this is not going to be much difficult now because I'm going to make this Hessian space big, but just in case we have products that we do. We have products again just for the cases of the of this bird, and the other two are going to be much easier. We'll see, okay? If we actually perform the derivative here in respect to x, this is a constant. So I just can write that at the beginning. 0.75 times 0.75 to the power of x, y. And then what happens is that y comes down again, and the logarithm of 0.75 comes down again. So this is square and square. Yeah, and so that is it. What about here? Well, pretty much the same. So we actually perform the derivative of this thinking of x, sorry, of y, it's going to be the same. X power of 2, Neperian logarithm, or natural logarithm to the power of 2 of 0.75 times 0.75 to the power of xy. Yes. But when we actually perform the other derivatives, this, there is a product. We have this, which is actually a constant, so that starts there, the imperial natural logarithm of 0.75, it's going to be multiplying everything, okay, because that is just a constant. And then we have these two members. First, the derivative of the first member, which is going to be 0.75 to the power of xy, and this is in respect of y, okay, so times x times the logarithm of 0.75 times second part without the derivative, okay, y, plus first part, which is this one, 0.75 to the power of xy, times the derivative of the second one, so this is just 1, and so that is it. I'm going to write it in red, so see, this all multiplies the Neperian logarithm of 0.75, and so what we have here actually is again something we can take as common factor, which is 0.75 power of xy. We can bring it down there or out there. So this is the Neperian logarithm of 0.75 times 0.75 to the power of xy, 0.75 to the power of xy, yes, times yeah, xy, I'm going to write it down because I'm not going to have a space there, times xy times logarithm of uh, 0.75 again, plus 1. And that is pretty much what it is, okay? That's it. The whole thing that goes in here and also in here. Okay? Yes. Let's go after number 5. Number 5. Let's see. And 5. Last one with just two variables. Okay? Okay, in this case we have 2y divided by x plus x. Cool. And so when we actually have the gradient of this, Usually the proper way to write it is like this, okay? Because I'm expressing that I'm gonna actually perform the derivative in respect of those two variables. I'm sorry, sometimes I forget these formalities. Anyhow, in respect to y, for example, first, okay, because it's gonna be easy. This is just 2 divided by x plus 0, which is 2 divided by x. What about what about x? Well, in this case, think that this is divided there, so it is a function. It doesn't matter because it's actually x to the power of minus 1, which is actually just, it's going to be negative, and it's going to be to the power of minus 2 instead of minus 1. But well, that is what it is. In this case, it's going to be minus 2y divided by x to the power of 2 plus 1. That is our function or our gradient and vector now. What about the Hessian matrix of F5? Also, actually here. Well, in this case, think when we think about doing this in respect to y, that's nothing. That is again 0. We'll do this in respect to x, which is, you'll see this in respect to x is which is which goes here is actually minus 2 divided by x squared, which is actually the same of actually of performing the derivative in respect to y here, because in respect to y this is just minus 2 by nothing, and x to the power of 2 is just a constant, and then plus 1 is plus nothing. Okay, what about the derivative of this one in respect to x? But whatever goes here, well, let's see. In this case, again, there is a, a quotient. The denominator, we have the function, so, or the variable we are actually performing the derivative in respect to. So this is x to the power of 4. I'm sorry I wrote it like that. No, like that. It doesn't fit, but it doesn't matter. Let's see. Okay. Yes. X to the power of 4. And then it's again negative, but as it was negative, now we have positive, and here is just 2y, because, well, it's just a constant, okay, and that goes there like that. Well, let's go after number 6, okay? In number 6, we have three variables, as I said, x, y, and z. And so we have e to the power x, y, z. Okay, and the gradient is in respect of these three variables, x, y, and of course z. And so here we have three partial derivatives. In the first case, yz times e to the power xyz. Of course, whatever is not the variable comes down because that's the derivative. Here is x z power b x y z times, and here is y, sorry, x xy, yeah, xy times e to the power xy z. Cool. The Hessian matrix is going to be a little bit more complicated, but yes, f6 x y z. Of course, before it was just a 2 by 2 matrix. Now it's a 3 by 3 matrix. So, yeah. Now it's just bigger, but it doesn't matter. And always think like this, okay? X, Y, and Z. And so in the main diagonal, we have the derivatives just repeating the variable twice. Okay, so this is Z, Z, Y, Y, and X, X. And the rest of places, just combining variables. And again, these two derivatives are going to be the same with these two. Same happens with these two. So you just have to actually do one. And the same happens with these two. They are going to be the same, okay? this is going to be xy, this is going to be x set, and this is going to be y set. So just those, okay? Look, um, main diagonal is going to be pretty straightforward because actually we never have the same variable and we are performing the derivative again. We don't have it here, so that's no product. That's just a constant in this case. And so we have y squared z squared times e to the power of x, y, z. Here we have x squared z squared to the power times e to the power of x, y, z. And here we have x squared, y squared, e to the power of x, y, z. That's what we have there, okay? What about the other ones? Well, let's see. Let's do, for example, f6 uh, first to x and then to y here, okay? And so here we have like that, we have set as a general constant, and then we have a product of y times e, okay? So we have first member and second member, and so if we apply this, the derivative of the first member in respect to y is 1 times e to the power of x, y, z, remember, not applying any derivative, plus first member without the derivative, which is y, times the second one applying the derivative, which is x e to the power of x, y, z, times x and z. That is it. And so, if you think about it, well, we'll see what we have here. And what we have is that the only variable that appears twice is this one. And so, I'm going to actually develop it a little bit more. This is going to be just set times e to the power of x, y, z plus x, y, z squared times e to the power of x, y, z. Yes, we can take common factor of this and also of one of the sets here. And this, well, I don't think it's really necessary. Maybe we can take the e to the power of x, y, z maybe better, but it doesn't matter. Here is just z plus x, y, z square, okay? It doesn't matter. The only thing I want is to see the commonality and the thing that actually makes this. The z doesn't appear here, and it's here, also here. So I can only assume that actually uh, this, so this is 6 right, of x, and then, for example, z is going to be just exactly the same, x, y, z times y plus x, y squared, z. And when I do this is just symmetric, so I can think this is going to be like that. And you can actually try, of course, y and then z is going to be just e to the power of x, y, z times x plus x squared y z. I'm I'm just thinking. And so, of course, uh, this xy thing, this one here, this goes here and here, this here, x, and then z goes here and here, and this last one with y and z go here and here. Okay? So we don't actually, this goes here, this goes here, and this goes here, and of course their counterparts. Okay, so that's number 6. Let's see number 7. Number 7, yes, f7 of x, y, z. This is the Neperian logarithm of x plus 2y plus 3 z squared. Okay, and then the gradient. Sometimes we are tempted with actually uh, applying this rule of logarithms that apply only to divisions or quotients or certainly and multiplications, and thinking that the sum of whatever is inside the logarithms is equal to the sum of logarithms. That is not true, okay? It's the multiplication is the logarithm by multiplication, which is actually the sum of the logarithms. But we'll see it a bit later, yeah, because we have an example in this set of exercises. In this case, look, this is always the same. This is just 1 divided by whatever is inside here all the time, because this is a function of x, y, and z. So all the time it's going to be the same, this and this, boom, boom. But this is always x plus 2y plus 3 z squared, x plus 2y plus 3 z squared, x plus 2y plus 3 z squared. Over here in the numerator, what's gonna be is the derivative of whatever is inside. In respect to x, this is actually 1. In respect to y, this is actually 2. And in respect to z, this is actually 6 z. And so that is the gradient. The denominator is the same, but the numerators change, okay? It's just a quotient with a little bit of a difference. Of course, now we have a function of, of these three variables, of course. And so we are just gonna work with them, okay? This case, the Hessian matrix of F7 of X, Y, so of X, Y, and Z is this. First, first one, in respect to X again, okay? It doesn't matter much, just maybe in the last case, but in all of them, the numerator is gonna be like it is, and it's the denominator what's gonna suffer a little bit. We have to do always this, okay? We have to do this. Um, yes, we have to actually think about the general rule of actual quotients with the derivatives. So in this first case, this is just minus 1 divided by the square of whatever is below. And so this is x plus 2y plus 3z squared, and this to the power of 2. The same here with y, okay? I'm sorry, because of the space. That's y z, x, y, z. This is just minus 2 divided by x plus 2y plus 3z squared to the power of 2. And last one is just the same. Difference actually is that, again, like in this case, we have to bring out the derivative of whatever is inside. And in this case, the derivative of 2y is actually 2. So this is actually 2 times 2, so this is 4. And the same happens in the last case, where we have to actually bring out the 3 times z times 2 squared. But, I mean, to the power of 2. But, last case, we have actually a function with set in the numerator. And so, we actually do that as the rule of the quotient. And I'm going to do it here, okay? This is f7, 2 times set and set, okay? In this case, we will go part by part, okay? In the denominator, yes, it's this to the power of 2, okay? Yes, and and in this case, look, what we have to do is actually, yeah, I'm gonna do it in blue, for example, is performing the normal rule of the derivative. So derivative of the first one, which is 6, this is in respect to set over time, times the second one with applying the derivative, so y plus 3 set to the power of 2, and now minus, all right? Minus the other part. Which one is the other part? Well, first member without applying the derivative times second member applying the derivative. And the derivative of the second member when thinking about z is just 6z. So it's actually 36 z squared, which is actually what yeah, what we have here. And so this is just 6 times x plus 2y plus 3z squared minus 36 z squared divided by x plus 2y plus 3 z to the power of 2. This is pretty much it. Okay, we could simplify that. I actually prefer not to because I usually tell you to actually leave it well, but without the simplification. Better, much better than simplified and wrong. Okay, this this goes here. Okay, this goes just there, just there. Rest of cases, well, rest of cases we actually have pretty much what we did in these first two cases, but uh, multiplying by the derivative in respect to whatever variable we have. So when we actually take the x part and apply the derivative in respect to y, we actually bring out the the 2. So this is minus 2 divided by whatever was in the denominator square. Okay, so this is I'm gonna write it out there and just point out that it goes there. Derivative of f7, second derivative, doing it first in respect to x and then in respect to y. This is just minus 2 divided by x plus 2y plus 3z squared to the power of 2. And that's what goes here. And of course, as it goes there, it also goes here. Because if you think about this one, it's going to be the same. It's going to be minus 2, and then the derivative of x is going to be 1. So exactly the same. Other two cases are a bit more complicated. Are again, other, yeah, xz and yz are going to be division rules. So it's going to be, again, a bit more complicated. It's going to be a division or a quotient. And so we have to apply the rule. And it's going to be a quotient because we have a something as a function here. And so that's going to be a little bit problematic. We're going to see, I'm going to bring it down. But the result is actually, I won't say obvious, but let's see. At least easier than I could say. Okay? X and then Z from here, Y, F7, F7, Y, and then Z. I'm gonna try and keep on seeing them. Okay, so this one. And so here we just have something in the denominator. Okay, so we could actually apply the function, but it is first. First is it's not necessary. We have minus one here, and then we have everything the same. X plus 2y plus 3z squared times, this is all to the power of 2, times the derivative of this part. So this is minus 6z. And so in the numerator, here is minus 6z. Well, not minus 6z, the minus is already there. So this is just 6z. And this is where it is. This goes, of course, here and also here, okay? This goes here. Sorry, I'm gonna do this. This goes here and also here in the Hessian matrix. What about the second one? Something really similar happens. Yes, because we just have, I'm gonna write here, a minus, in this case 2, divided by x plus 2y plus 3z to the power of 2, all of it to the power of 2, and then times 6z. So here we have minus 12z. and that is just the whole thing. And so this goes here and also here in these two positions here. I'm sorry, sometimes it's not so, but I would have to make a very huge matrix for all of these to actually fit in. And so I think it's easier to actually have it like this. Okay? And so this is, well, this is what it is. Okay? This is the whole thing. Well, let's go after number 8. Number 8 is 8 x, y, z. It's actually x divided by z plus y divided by x plus z x divided by y. Cool. The gradient of f in respect of x, y, z is actually this one, which is in respect to x, this is 1 divided by z, this is minus y divided x squared, and this is z divided by y. Second one, y. Well, y is just 1 divided by x and minus z x divided by y squared. Last one, z is just minus x divided by z squared plus x divided by y. This is the whole gradient, and the Hessian is also, I think, as easy as this one. Okay, and this is Hessian of f8 in respect of x, y, z. Let's see. I'm gonna try and make it b. Okay, remember x, y, z. But I can do this in respect to x, in respect to y, and in respect to z. So this first one, in respect to actually to x, is just pretty much nothing, because 1 divided by z just goes, z divided by y just goes, and here we have just where it is. Here we have, and as we saw before, what we have to do here is actually do this minus minus, which is plus. Okay, this is actually positive now. The y keeps there, and then divided by x squared, and now times the derivative of this. Of course, this is to the power of 2 again, and now times the derivative of this, which is 2x. And so 1 degree of this exponent just goes, and a 2 keeps here. So this is just 2, and then instead of a 4 here, we have a 3. Yeah, just as we did before. Okay, second one, uh, here in respect to y, something similar happens. This is plus zx divided by y to the power of 4 times 2y. So this is going to be y to the power of 3, and now a2 goes there. What about z? Well, something similar. It's going to be plus x divided by z to the power of 3, and then a2 is going to come out here, uh, just like that, okay? What about the rest? Well, we'll see. Um, for example, second one, uh, in respect to first one, sorry, in respect to y, for example, okay? In respect to y, we have minus 1 divided by x squared, and then minus z divided y squared. Okay, just easy like that. What about here, for example? Let's see if we have the same actually. What about this one in respect to x? We have minus 1 in respect to x squared minus, and now just z divided by square. Of course, it's going to be the same. I know it, but I just wanted to show you that these two are actually the same. Although sometimes it doesn't look like they're gonna get to the same point, but well, they do. First one in respect to set. This is minus 1 divided set square. Nothing with this. And here is just plus 1 divided by y. So same here, okay? Minus 1 divided by set square plus 1 divided by y. And second one in respect to set. I don't do nothing, the first part, and here is just minus x divided by y squared, and here the same, y x divided y squared. So this is pretty much the whole Hessian matrix. In this case, I knew they were small, so that's I could fit the matrix there. And so here it is. Now number 9 and then number 10. We are done with it, okay? Well, number 9. Number 9 is this one, which is the natural logarithm of x times y squared divided by z power of 3. Okay? And yes, here you have to apply, well, you don't have to, but it's much better if you apply the rule of the logarithms. And so here, instead of having this quotient here, you have three different logarithms. You have the logarithm of x plus the logarithm of y squared, which is something else now, minus the logarithm of z to the power of 3. And also, we can bring down these exponents and have them multiplicating the logarithms. That's also a rule of the logarithms. And so this whole f9 becomes actually the logarithm of x plus 2 times the logarithm of y minus 3 times the logarithm of z. And so actually the gradient and also the Hessian matrix um, end up being pretty straightforward. Okay, let's see. Doing it like this, I just with respect to x, 1 divided by x, 2 divided by y, and minus 3 divided by z. That is all. That is my gradient. Because in respect to any of them, I don't have any common function. These are sums or additions. So the derivative is just like it is. The Hessian matrix of F9 is just C. All that is not the main diagonal is 0, 0, 0, 0, 0, 0. Why? Because I don't have any y or x here or z here. I don't have any x or z here. I don't have any x or y here. So 0, 0, 0. What about the rest? Well, minus 1 divided by x squared, minus 2 divided by y squared, and plus 3 divided by z squared. And that is pretty much the whole Hessian matrix. I just apply the rule of the quotient if I want, or just 1 divided by something, which is actually just like that. And well, last one, which is a sum of square roots, x, y, z, um, x plus y plus z, okay? And this is just uh, again something similar as before. I usually write this as this to the power of 1/2 or 0.5 y to the power of 1/2 plus z to the power of 1/2. And so the gradient of f10 is just, well, this is 1/2 of x to the power of minus 1/2, 1/2 of y to the power of minus 1/2, and 1/2 to the power of z to the power, sorry, times z to the power of minus 1/2. I'm so sorry. And yes, again, the Hessian matrix of F10 is going to be just a bunch of zeros and a main diagonal that has numbers. That, remember, is a diagonal matrix. And so this is just that. that, yes, because we don't have any y or z here, we don't have any x or z here, and we don't have any x or y here. And so all of those are zeros. And let's see, here is just minus 1/4 of x to the power of minus 3 halves. Same with all of them. Minus 1/4 times y to the power of minus 3 halves and minus 1/4 to the power of z, sorry, times the z to the power of minus 3 halves. And that is pretty much the whole thing. And that is it. I'm gonna go through all of them, okay? It's just a sum of square roots. I think it's obvious. This one, once you divide the logarithm or just separate all its components, becomes much easier. Here, careful with remembering to actually do the multiplying everything by the derivative of whatever is below. Same thing here. Remember, okay? That is kind of the key there, okay? It's just like here. Ah, well, I see here that I can do that. Yeah. Here, we actually have to multiply this by 2x. And so this is just x to the power of 3, and this is just 4, right? Yeah, well, this is just the top of my mind. I think, yeah, I think it's right. But anyhow, if I made any other mistake, well, it's just an honest mistake. Of course, I'm doing this just to help you. If you find any mistake, just point it out in the comments, okay? If you think, or just tell me in class or something. Um, this is just a logarithm without the e, which is, I mean, it's just an exponent without the e, and you have to bring down the logarithm, but it's just not so complicated. Here with the y and the e to the power of x, here is actually the important thing here is to actually see that this first function actually is the same as after performing the derivative in respect to x. So once you've done that, the rest, the Hessian is actually a second gradient because this doesn't change. And in respect to when you perform the derivative of the second one in respect to y, there's nothing. So there's a zero. Here is just kind of the same. Just um, yeah, e to the power of something, and then you have their products that actually make your second derivative, second order derivative a bit more difficult, but not that much. And here is just the application of the sine and cosine. I know the sine and cosine trigonometric functions sometimes are not seen in economics and mathematics for economics. But, well, it's just a simple rule from sine, cosine, and from cosine minus sine. So that is pretty much the whole thing. Anyhow, thank you for your attention, and I hope this was useful. Bye.